All right, so let's see some examples. So these directions say find the values of the 6 trigonometric functions for angle theta, right? So we're given this triangle here, and we know that these are the 6 trig functions, right? So we're going to try to find all those, right? Now, one thing is here, remember that these are ratios of 3 sides, but one of these sides is missing, right? We're missing, like if this is theta, first of all, let's start with the hypotenuse. So this is the right triangle, or the right angle, excuse me. And so in a right triangle, the side that's opposite of the right angle is called the hypotenuse. Okay, so this is the hypotenuse here. And then the one that's opposite of theta is called opposite, the one that's across. And then the one that's next to is the adjacent side, right? So this is the one that's next to theta, the leg that's next to theta, so this is called the adjacent, right? And by the way, I forgot to mention before, so you do have your hypotenuse, and then you have your legs, okay? So the ones that form the right angle, the ones that make the right angle, those are the legs, and then the one that is across from the right angle is the hypotenuse, okay? So those are just some terms that you'll hear used, and you probably know those already. All right, so the problem here is we're missing adjacent, right? So when I try to find anything with adjacent in it, I'm going to be, I won't have a value there. So we know that when we have a right triangle, we can find any missing side we want, right? Because we know the Pythagorean theorem. So we can say, okay, well, we know a squared plus b squared equals c squared, right? Where c is the hypotenuse and a and b are the legs. And so I can say, okay, well, let's let adjacent be A, right? So we'll let this be adjacent, and then we'll plug in 5 for B, which is the opposite, right? And then we'll plug in 13 for C, which is the hypotenuse. And then we can solve for A. So we'll say A squared plus 5 squared equals 13 squared, right? So 5 squared is 25. 13 squared is 169. We can subtract 25 from both sides. So we get a squared equals 169 minus 25 is 144. Then we can take the square root of both sides, right? And we know we're going to return a principal value. So we're not going to do a plus or minus this time because we're talking about the actual length of a triangle, right? So it doesn't make sense for it to be negative in this context. And so we're not going to put the plus or minus here, okay? So keep that in mind because we have some context, right? So we're just going to use the positive value, which is 12. So that's what the adjacent is 12. All right? So now when I find my trig functions, now I have everything I need, right? So if I'm trying to find sine of theta, right? This is the reference angle theta. And so, yeah, whatever you put in here represents your reference angle, right? And so sine is opposite over hypotenuse. So that's the so part of SOHCAHTOA. Opposite over hypotenuse. So it'd be 5 over 13. And then if you can reduce, if not, that's it. Okay, 5 over 13 can't reduce. So we leave it like that. Cosine of theta is adjacent over hypotenuse, right? So here's adjacent 12. That's going to go in the numerator. And hypotenuse 13. So that's going to go in the denominator. All right, and then we have tangent, which is opposite over adjacent. So opposite 5 over adjacent 12. Okay, so there's our main 3 trig functions. So now let's find the reciprocal functions. So cosecant, all I have to do is flip this over, right? Cosecant is the reciprocal of sine, so it's just going to be 13 over 5. Secant is the reciprocal of cosine, and so it's going to be 13 over 12, right? Or hypotenuse over adjacent. So you can do it that way too, hypotenuse over adjacent, or you can just flip over cosine, right? Whatever is easier for you. And then cotangent is the reciprocal of tangent, so we just have to flip over tangent. So it'll be 12 over 5. Or you can look over here and say, okay, it's adjacent 12 over opposite 5, right? Either way works. All right, so that's it. So really, all this exercise, this particular example is doing, is just helping us to understand. Okay, first of all, what are the what's the anatomy of this particular right triangle, right? What's the adjacent, opposite, and hypotenuse? So we understand that. We found the missing side there using Pythagorean theorem, and then once we found that, then we just set up our ratios. So we put we just put opposite, adjacent, and hypotenuse in their particular locations, right? With respect to each ratio. All right. Okay, so let's check out number 2. Number 2 is going to be a little more work because this is what's called a Pythagorean triple, when all your sides of a right triangle come out to whole numbers. Number 2, that's not the case. So we're going to see some radicals, and luckily we know how to work with radicals, right? So we'll see that here. So first of all, I want to identify my side. So here's the right angle. So hypotenuse is across from that, and actually we're missing hypotenuse, so we need to find that. Then opposite is across from theta, so this is opposite. And then adjacent is the one that's right next to theta, the leg that's right next to theta, right? So this is adjacent here, the 2. All right, so let's find hypotenuse. So I want to say, I know a squared plus b squared equals c squared. This time we're missing c, right? So this time I'm going to plug in 2 for a, 3 for b, and then c is what's missing here. That's a question mark. And so it'll be 2 squared plus 3 squared equals c squared. So this will be 4 plus 9 equals c squared. 13 equals c squared. So then we'll take the square root of 13 on both sides. And we can't simplify that, right? 13 is prime. So it's just going to be c equals root 13. And that's fine. Just leave it like that. So we know that hypotenuse is root 13. So let's find all our ratios. So first of all, sine. SOHCAHTOA, sine is opposite over hypotenuse. So it's going to be 3 opposite over hypotenuse root 13. All right, so 3 over root 13. And that's our ratio. But remember that there's an issue when we have a radical in the denominator, right? And so we want to rationalize the denominator whenever that happens. And so so in this case, it's root 13 on the bottom, square root. So all I have to do with the square root is multiply it by itself, and that cancels out the square root, right? And so what this will turn into is 3 root 13 over 13, okay? All right, so that's sine of theta. Okay. Next, cosine. So cosine is, that's the ca part of SOHCAHTOA, C-A-H, and that's adjacent over hypotenuse. So it's 2 over root 13. And you can probably imagine what's going to happen. We're going to multiply by root 13 on top and bottom in order to rationalize the denominator, right? So on top we get 2 root 13, and on the bottom, root 13 times itself is just regular 13. Okay, so that's cosine. Then tangent. Tangent is opposite over adjacent, right? So opposite 3, that's the TOA part of SOHCAHTOA. So opposite is 3, and adjacent is 2. So 3 over 2. So we don't have to rationalize that. It's good the way it is. It's reduced. All right. So now for our reciprocal functions. Now for our reciprocal, we can just flip over what we got with our original trig functions, right? But instead of flipping this over and having a radical in the denominator, I'm just going to flip that original over in this case. And so it's going to be root 13 over 3. Or you can think of it as hypotenuse over opposite, right? So root 13 over 3. So we can think about it either way. Okay, so for secant, Secant is hypotenuse over adjacent, so it'll be root 13 over 2, right? And that has a rationalized denominator. So we could have just flipped this over 2 is another way to get it. Okay, and then finally, we're looking for cotangent. And so we can just flip over tangent, or we can do adjacent over opposite, right? Either way. So it's going to be 2/3. All right, and so that's how we find the 6 trig functions given a right triangle, right? Even if we only have 2 sides, we can find the third using Pythagorean theorem, and then we can, once we get that, we can just plug them into our ratios. Sometimes you might have to rationalize the denominator, no big deal. All right, and that's it. So that's how you define the basic 6 trig functions, or the 6 trig functions.